Good morning, dear students. In this video, I would like to discuss with you about counters. Counters are used to perform counting operation. Therefore, if group of flip-flop that can be connected to perform counting operations are said to be counters. So, the building block of counters is flip-flops. The counters driven by a clock can be used to count the number of clock cycles. So, we are using each clock pulse to count. If a counter consists of n flip-flops, then it may be count pulse up to 2 raised to n. For example, if we are using 3 flip-flops, we can count 2 raised to 3. That means 8 digits from 0 to 7. If we want to count more, we have to use more flip-flops, like 4 flip-flops to 16 counts, 5 flip-flops for 32 counts, like that. Now, the counters are classified into asynchronous or ripple counters and synchronous counters. Let us check asynchronous counter first. It is also called ripple counter. If the flip-flop do not receive the same clock signal, then that counter is called asynchronous counter. The outputs of system clock is applied as clock signal only to first flip-flop. So in this asynchronous counter, if we are using 3 flip-flop, the clock pulse is given only to the first flip-flop. The remaining flip-flops receive the clock signal from the output of its previous stage flip-flop. So, all other flip-flops using the output of the previous flip-flop as clock. Hence, the output of all flip-flops do not change effect at the same time. So, it's called asynchronous counter. This is the logic diagram of asynchronous counter, in which we are using 3 flip-flops. So, we can count from 000 to 111. That means binary numbers 000 to 111. In decimal, it means from 0 to 7. For that, we need 3 flip-flops. All flip-flops used here are JK flip-flops, in which both J and K are connected common to plus VCC, or we keep it always high. So when we check this circuit diagram, all these J and K inputs are connected to a common plus VCC. The first flip-flop we are using a direct clock pulse, that is negative triggering. That means this flip-flop active only when the clock pulse is negative triggered. Now, for second and third flip-flop, we are connecting the outputs of the corresponding previous flip-flop as the clock pulse. So, for the second flip-flop F1, we are using the output of F of 0. And for the third flip-flop FF2, we are using the output of FF1 as the clock signal. Remember, in all cases, we are using the negative edge. And the final outputs are C, B, A. That is Q2 as C, Q1 as B, and Q0 as A. Remember, C is the most significant bit and A is the least significant bit. So, when we convert it into numbers, binary number, it's not A, B, C. We call it as C, B, A, from right to left. So, in the case of asynchronous counters, the flip-flop used are negative edge trigger type. So the state of each flip-flop will change at the negative going edge of the clock pulse. Initially, all the flip-flops are cleared by applying a clear pulse on the CLR line so that A, B, C is equal to 0 and count is 0. Now, the clock pulse is applied to the first flip-flop. So, initially, A is equal to 0, B is equal to 0 and C is equal to 0. I am giving a clock pulse so that this first flip-flop gets activated, and we know when J is equal to K is equal to 1 is the toggle condition for JK flip-flop. That means it will invert its output when we are giving J is equal to K is equal to 1. So, in this type of counters, we are keeping J is equal to K is equal to 1. Therefore, whenever a negative pulse is given to this flip-flop as clock, it will change its state or it will invert its state. Therefore, during the first clock pulse, it's changed its state from 0 to 1. Then this 1 is fed to this second flip-flop. It will not be activated because to get it activated, we need to give a negative pulse. And for the third flip-flop, even though this is 0, it's not a pulse, it's a continuous state. So it is also in the deactivated state. Therefore, the final output is most significant bit is 0, then B here 0 and 1. Therefore, 0, 0, 1 stands for first count. Our state after first count is 0, 0, 1. Then I am giving second clock. When I am giving the second clock, the low or negative triggering clock, the output get inverted because J is equal to K is equal to 1. Therefore, A changes to 0. So, this 0 comes here and it will get activated by this clock pulse and changes to 1 because here it is 0 and it will get inverted. And this 1 is given, and this one is given as a clock signal to the third flip-flop, but this is high, so it is in the inactivated state. So the count is CBA is 0, 1, 0, 0, 1, 0 equivalent to count 2 in decimal. So in the next clock pulse, during the negative triggering urge, Q0 changes from 0 to 1. High goes to the second flip-flop as clock, so there is no change. This high goes here, no change. Therefore, the final output is 0, 1, 1, 3, equivalent to 3 in decimal. Like that, as we are giving the clock one by one, this will count up to 7 or 1, 1, 1. These all things are written here. I already discussed it with a logic diagram. So during second clock pulse, FF0 toggles from 1 to 0 state. Output A goes from 1 to 0. At this negative going edge of the output pulse, the flip-flop F11 changes state. That is, the output of B goes from 0 to 1. So at the end of second clock pulse, the count is 0, 1, 0, which corresponds to count 2. Similarly, when third clock pulse arrives, A changes to 1, then B remains same, C is equal to 0. So after third clock pulse, the output is or count is CBA 110 corresponds to count 3. So the counting continues to take place for the arrival of each clock pulse as input. The output state for the successive pulses are shown in the truth table. I will show it soon. At the negative edge of the 7th clock pulse, the flip-flop output are all high. That is CBA is equal to 1, 1, 1. When the 8th clock pulse arrives, all flip-flop reaches to 0. That is CBA is equal to 0, 0, 0. Therefore, this 3-bit counter have 3 flip-flops, and we can count from the decimal 0 to 7, or in binary from 000 to 111. This is the truth table of 3-bit counter in which the outputs are ZBA. So this is the negative triggering clock pulse. When we are giving 0, or before starting, the output is 000. After first clock, it changes to 001, second 010, and so on. And finally, after the 7th clock pulse, the output is 111. This is the timing diagram of 3-bit asynchronous counter in which we are giving clock pulses, 8 clock pulses, and remember the output states will get changed in the negative triggering part. Therefore, outputs QC, QB, and QA are represented as CBA, and we know after each clock pulse, the first A state changes or toggle state. So during the negative triggering edge of first clock cycle, Q goes to high and it continues up to the next low. That means up to the low state of 2. Then it goes low. Then the 3rd clock cycle in the negative earth, it goes to high. 4th goes to low. In the 5th negative earth goes to high, low, high, and like that. And when we consider the second output B, or second digit, here we can see it goes to high at 2 and 3, and also at 6 and 7. So during the second clock pulse, or the negative edge of the second clock pulse, it goes to high and continue there up to 4th. 4th means the low state of 4th. Then it goes to high at 6th and 7th. It goes to high at the low or negative triggering edge of 6th and 7th clock pulse and continue like that. And when we consider C, it is low up to 3rd clock pulse, and it goes to a high state at 4th clock pulse. So during the negative edge of the 4th clock pulse, it goes to high. So you can easily draw this diagram with the help of this truth table. This is all about asynchronous counter or ripple counter. Thank you for listening. Thank you.